Okay, so this is a Unit 5 problem, and this is the electrochemical cell series. So if you haven't learned anything about it, it's just that, just know that these values of E cell, the half cell equations, they're always given as a reduction. You can see that they're all gaining electrons, and gaining electrons is reduction. So these are all called basically reduction potentials. So these are all reduction potentials. But what's going to happen is if one of them is being reduced and the other is being oxidized, so what we have to do is we have to manually flip them. So if this guy was being reduced by this guy, what I would do is, as this is being reduced, if this is being reduced, so I'll leave it as it is because this is a reduction potential. If this guy is oxidizing this guy, so I have to flip this, right? So V2 plus is going to come to the left. So let me write it down very quick. So this guy is now being reduced. And when I'm reducing it, I have to flip the sign. So this becomes positive. And then if I see the E cell value, then the E cell value, this is unchanged because I'm going to leave it as it is. And then this is going to be flipped, 0.26. So I can see there is some negative value. So as if E cell is negative, that reaction is not feasible. That reaction is not feasible. So that reaction is not going to happen. That is thermodynamically not feasible. That reaction is not going to happen. So that's that. So I'm going to get rid of these. So that's a quick basic for you guys. So if this is hard for you to understand, just remember that whatever you're reducing, it's going to be on the right-hand side. Whatever you're reducing, it's always going to be the formula like this. Always remember this formula if it's hard. So if one species is being reduced, so you're going to have the E value of the reducing species minus the E value of the oxidizing species. So that way you always flip its sign. That is the E cell formula, if that is hard for you to understand. So that's that. Okay, so let's go to the problem. So in this part here, it asks us to go into the data booklet and fill the table up. So I've already done that. This is plus 1.36. And from the data booklet, it's going to be the reduction of Fe3 plus ions. It's going to gain electron to Fe2 plus ions. So like I said, this is very important to understand that we always represent the half equations as reduction potentials. These are all reduction, right? These are all reduction. So this is very important to realize. Okay, so the B1, question B1 asks us to find the most powerful reducing agent. So a reducing agent itself is going to get oxidized. So it's going to get oxidized. It means that it's going to lose electron. It's going to lose electron. But if we look into our table, we're gaining electron. These guys are gaining electron. So the higher the reduction potential of any species is, the more tendency it has to be reduced. So we're basically looking for the lowest reduction potential value. So in this case, the lowest reduction potential value is minus 0.76, which is this guy. So this basically means that zinc 2 plus ions do not want to get reduced to zinc. What it instead would prefer is the zinc metal would become oxidized to zinc 2 plus ions by losing 2 electrons, and then this would become positive. So that's what it wants. So the answer to this is always remember that the most powerful reducing agent is going to be the lowest, the most negative number in your table. So in this case, so as the reverse is going to happen, the answer is zinc, the zinc solid, not the zinc 2 plus ions. Don't write that, because when I'm flipping the equation, zinc S is coming to the reactant side. It's coming to the left. So this is reacting. The zinc 2 plus ion is not reacting anymore, right? It's the product. Okay, then we move on to the next one. The species which in acidic solution will reduce VO2 plus to V3 plus. So this is vanadium 4. Vanadium 4 being reduced to vanadium 3 plus, but it will not reduce vanadium 3 to vanadium 2. Okay, so we've already talked about this here, so I'm going to write it here. So E cell, the E cell is always the guy being reduced, the E value of the guy being reduced, minus the E value of the guy being oxidized. So for this part, I know that the E cell is equal to the guy being reduced here is this VO2 plus to V3 plus, which is here. VO2 plus to V3 plus, the value is plus 0.34. So I'm going to come down here and I'm going to write plus 0.34 minus whatever is going to be here. This is the unknown. And for this, so we know that this was reduced. So that means that the E cell was positive. So I'm just going to write a positive. I'm just going to mention that this value, whatever the value was, it was a positive value. So in order for the E cell to be positive, this number here can be either this number here can be either a positive number that is less than 0.34, or it can be any negative number, right? It can be any negative number. So if you put like -2, so minus times minus is going to be positive, the E cell is going to be positive. But if you add a positive number that is larger than 0.34, what's going to happen? Say I'm going to put +1. So what's going to happen? It's going to become, the E cell is going to be negative, so that doesn't work. So that from here I know that it's going to be a positive number that is less than 0.34, or it can be any negative number. So I go back here, a positive number less than 0.4, this is 1, and these are the two negative numbers. So any of these three. So then I move on to the next hint. It can reduce V3 to V2. So it can reduce V3 to V2. So this is out of the question now. So it is not that I know, because this is the guy being tested. So it can't react with itself, right? So this is gone. So I have two options, right? So if I write the E cell again, the E cell is going to be the E reduced. This is for the second part, minus the E oxidized. So my E reduced value, so this is for the V3 to V2. The V3 to V2 was minus 0.26. So this is going to be minus 0.26 minus whatever the value is going to be here. So I know that this doesn't happen, right? So my E cell is negative now. So in order for this to become negative, I cannot have, well, I can have a negative number that is in magnitude, it has to be more than 0.26, right? So it can be negative 0.4. So if I put negative 0.4, then this guy becomes positive, right? Negative, negative, and this guy becomes positive. So I know that the other negative number here is 0.76. So if I put 0.76, if I put negative 0.76, this thing becomes positive, but that doesn't happen, right? This reaction doesn't happen. So it cannot be this one. It cannot be this one. So the only option you're left with is positive 0.17. So to test the theory, let me add it here. So let me add positive 0.17. So now I see it is still negative. So it is negative 0.09, right? If I'm correct. So anyway, it's a negative number. So this doesn't happen. So this 0.17 satisfies both. So this satisfies both. So the answer is this one. So this guy, 0.17, this is the one. So notice that this is being oxidized, right? So you have to flip this. So if you flip it, this guy is the species that's reacting with SO3 2 minus. So your answer here is gonna be SO3 2 minus. And then we move on to the next one. So you added zinc powder and you formed a mauve solution. You added zinc powder that had VO2 plus ions. And so if you go into the chart, you know that lavender and mauve, these are the same thing basically. So right away you know that this was produced. So your zinc reduced the vanadium 5. This is V. The oxidation state of vanadium here is +5. So the +5 vanadium got reduced to +2. So that's that. So now what you have to do is you have to write an overall half equation for the reduction of this guy to V2 plus. So the way we're going to do it is we're going to go to the table, we're going to start off with this one. So VO2 plus 2H plus. So, oh, let me just bring it down here. So it's going to help me. I guess I can't. Okay. So the half equation was so just bear with me, plus E minus plus water and the other one was VO2 plus V3 plus. Okay. This is the other one. This is vanadium 4 being reduced to vanadium 3 plus and water. And lastly, the vanadium 3 plus is going to gain electron and become vanadium 2 plus. So we just need to write the overall equation. So what we do is we cancel stuff wherever possible. So V3 plus is going to cancel out because they're on the opposite side. VO2 plus and this VO2 plus are going to cancel out. They're on the opposite side. And then we simply add everything up. So this is VO2 plus 2H plus. So we're going to add the 2 H's. So this is going to be 4H plus. So this is going to be 4H plus. Then we're going to add all the electrons up. So this is 3E minus. And then we're going to have V2 plus 2H2O. So for this equation, we can also add the E values. So I know that for the first one, it was +1. This was +1. For the second one, it was 0.34 and then -0.26. So this is 0.34 and this is -0.26. So the E value for this overall guy is just going to be the summation of these guys. So you can do that. So 1.34 minus 0.26 is going to be plus 1.08. So if that's needed. So what's going to happen is I'm going to recap. So this is the +5 vanadium being reduced to +4. This is the +4 being reduced to +3. And this is the +3 being reduced to +2. So now you have the overall, the +5 being reduced to +2. So this is your answer for that part. So the oxidation number in the final species, I know that it was mauve in color, which was lavender, so it was 2 plus. And the half equation is this. Then we move on. So while it was still warm, it was filtered, and during the filtration, the solution became green. On standing for some time, the solution turned blue. So what's happening is So green and blue, let's go and check. So green is 3 plus, blue is 4 plus. So basically the 2 plus vanadium is getting oxidized back to plus 4 state. By what though? It's getting oxidized by the oxygen in the air. The oxygen in the air is oxidizing it back. So explain these color changes and write two half equations. So what's happening is the V2 is being oxidized by the oxygen to V3 plus. So I'm going to write the V2 plus is being oxidized, so it's losing electron and becoming this, right? And the oxygen's half equation is this. The oxygen in the air is being reduced. So O2 plus 4H plus 4, so I'm going to write this down. So this is becoming, so this is that. So in order to write the overall equation, I need to cancel the electrons. I need to multiply this guy by 4. And then the overall equation is going to be 4V2 plus O2 plus 4H plus and then the electrons are going to cancel out. I don't have any electrons here anymore. So I have 4V3 plus 2 water. So this is the overall equation of it being oxidized from 2 to 3. And then from 3 to 4. So I go back. So I have the 4 to 3, so I'll just flip it. So 3 to 4 is going to be, so V3 plus. So it's going to be, so it's going to be this. So again, it's going to react with the water. So this, it's going to react with the oxygen. So I'm going to write this equation down here. To cancel the electrons, I'm going to multiply this guy by 4. The electrons are going to cancel out. So notice that the waters are going to cancel out too. So I have 4 waters here and I have 2 waters here. So I'll have 2 waters left here. Plus O2. And then the H's are going to cancel out. No, it's not going to cancel out. So it's going to cancel out completely. That's what I mean. So I have 8 H pluses here when I multiply it by 4, and I have 4 here, so I'm going to have 4 H pluses here. So 4 VO2 plus 4 H plus. So that's the overall equation for that one. So we have to calculate the E cell values for this guy. So I'm just going to plug in the E cell values here. So the V2 to V3 is going to be positive 0.26. So this is going to be positive 0.26. And the oxidation, the reduction of oxygen is going to be plus 1.23. So it's going to be plus 1.23. So if I add them up, I have more plus 1.49. So this happens, right? As the E cell is positive, this reaction is going to happen. For this case, the value is the opposite. V3 becoming V4. So it's going to be minus 0.34. So it's going to be minus 0.34. And then the reduction of oxygen is going to be 1.23. So if I add them up, it's going to be positive 0. It's going to be positive 0.89. So this is positive 2. This happens too. So those are the two equations you need. So that explains the color changes. So the color changes, if you remember the colors, so it went from mauve to green and then from green to blue. So this is the mauve to green reaction, and this is the green to blue reaction. So instead of just scrolling up and down continuously, what I've done is I've just copied it down back here. So what this question is asking us is, well, you have already jumped from the V2 plus was already oxidized by the oxygen in air to V3 plus, and the V3 plus was oxidized to V4 plus, and now it's asking this reaction, the V4 to V5, is possible, but it doesn't happen. Why so? Right? Might be expected to change. So why is it expected to change? We can see. So if for V4 plus becoming V5 plus, let us write the equation. So the VO2 plus. I'm gonna avoid writing the state symbols, but you have to write them in your exam. So this is the half equation for 4 to 5, 4 being oxidized to 5, and the oxygen in air is gonna get reduced. So that's that. So in order to cancel the electrons, I multiply this guy by 4, and then I write the overall equation. So when I multiply by 4, the electrons are going to cancel out. So 4 VO2 plus O2 plus 4 water. So I can get rid of the water now. So if I get rid of the water, the 4 molecules of water here and the 2 molecules of metals here are going to cancel out, and then I'm going to have only 2 water there. And then I'm going to have 4 VO2 plus. These guys are going to cancel out. I have 4 of these here, I have 8 of these, so I'm going to have 4 H pluses here, 4 H pluses there. So that's that. This is the overall equation. And if we see the table, so the reduction value for this guy is going to be negative. So this is negative because this is we're oxidizing it. So this is negative 1.00, and for the oxygen, it is getting reduced. I'm not going to change its sign. So if I do the overall here, it's going to be positive 0.23. So yeah, this reaction is feasible, right? Because the E cell for this reaction is positive. So this reaction is thermodynamically feasible. But it's not happening. So if any reaction is thermodynamically feasible, but it's not happening, in A levels, you can just go ahead straight and say that this reaction is kinetically stable. That means the activation energy is too high. That's why this reaction is not happening. So this is, you can pretty much say this all the time. Whenever you see any reaction that is thermodynamically feasible but doesn't happen, what's the reason? It's kinetically